This week we're going to look at Riemann sums and the definite integral. So we'll start with Riemann sums. And basically what this is we're just going to be adding up the areas of rectangles and trapezoids. And that's really the whole core of this. Now there's going to be a lot of notation in here that you'll start to understand probably the more examples that we do. But don't worry too much about the notation yet. Just make sure you understand the concept. So here you have this picture. It says below is the graph of the function f of x equals 1 minus x squared, square root of that. So, and we have a quarter circle from 0 to 1. And it says on top of the sketch, draw rectangles that represent the left endpoint Riemann sum approximation with n equals 5 to the area A under this graph from x equals 0 to x equals 1. So what you're going to do is draw rectangles that have the left upper endpoint touching the function. So I'm going to use rectangles like this, and I'm just going to move these into place. So it says with n equals 5. So this part tells me that there's 5 rectangles. So I'm going to make 5 divisions. And that left endpoint needs to be on the circle. And if we have a x is from 0 to 1, 1 divided by 5 is going to be 0.2. So each of these will be 0.2 wide. And so we'll have the left endpoint, that is the endpoint we're talking about. So I'm going to draw 5 of these things, where the left upper endpoint touches the circle, and they're about 0.2 wide. I'll get a good one, hold on. Oh. Okay, there we go. So there's a third one. Upper endpoint touches the circle, and it's 0.2 wide. Last one, try to get that to be rectangular, and there it is. Okay, the left endpoint touches, and then I'm just going to mark these left endpoints of each rectangle. So now the B part. Will your above calculation represent an overestimate or an underestimate of the above area? So you can see in this image, all of these rectangles with left hand endpoints, all of the rectangles are over the curve. So it's obvious that's an overestimate. So that's an overestimate. And more than that, we can generalize that if you have a decreasing concave down function and you use left hand Riemann sums, you will get an overestimate. So in the next part, it says calculate the Riemann sum represented in your above picture to approximate the area under f of x. Give a numerical answer with at least 4 digits to the right of the decimal point. So what we're doing in this picture is really just finding the area of each individual rectangle and adding them together. What I'm going to do is give you the summation notation, notation so that you can start looking at that and maybe So in the C part, it says calculate the Riemann sum represented in your above picture to approximate the area under f of x. Give a numerical answer with at least 4 digits to the right of the decimal point. So let's go to the picture. All this means Riemann sums, we're just adding up the rectangle areas. So we can see that each of those has a width of 0.2, and the height is determined by that left hand endpoint. So I'm going to copy some of these things down here. So I'll write out f of x is the square root of 1 minus x squared. And then how about first thing we'll do is just calculate the areas of those rectangles. So each of them has a width of 0.2. So rather than multiplying 0.2 by every single rectangle, I'm just going to leave it out here, and then we'll add up the heights and then multiply them all by 0.2. So if I'm looking at this point right here, that would represent f of 0. This point right here would be f of 0.2. This point here is f of 0.4. And those are just going to increase by 0.2 every time. F of 1 at the end. Oh, actually, we don't calculate that one because that's not a left-hand endpoint. So we should have 5 rectangles and 5 values there. So all I'm going to do is write those down right here. So this would be f of 0, f of 0.2, f of 0.4, f of 0.6, and f of 0.8. So I should have 5 values in there, all multiplied by 0.2, which is the width of each rectangle. So this, when I calculate that, and just to clarify each of these, so like for f of 0, I'd plug a 0 into my function, for x right here, and then I would get a value out. So I've already calculated these to save a little time, and this comes to 0.8590. It says 4 digits, so I'll put a 0 there. I think it was probably a different number, but it's an estimate. So this is units squared. So if we go up there, it's going to be under 1, because if this whole thing were just a square, it would be 1 times 1. So 0.859 is a pretty good estimate. Or not a pretty good estimate, it's an estimate. And what I'm going to talk about here is summation notation. So this will be the left-hand sum. And this is new notation. You've probably never seen it before, or if you've seen it, you didn't know how to use it. So this is a sigma. And this is not the sum for this one. This is the generic formula. Okay, so I'm gonna write these out for each of these, and for this assignment, for the next assignment, you don't have to use this yet, but I do want you to start looking at it. So this formula has a lot of parts, and let's just do this. I'll call each of these parts what they are. So n is number of rectangles. Okay, so in this case, we'd plug a 5 in there. A is going to be your first value that we're using. So in our case, A would be 0. J would represent, it's an index number, so we're going to count up 5 rectangles. And so J is going to start on 0, and we'll count up 0, 1, 2, 3, 4, because that's 5 altogether. 0 through 4 represents 5 different values. Delta X is the width of rectangles. Okay, and this part here is your function evaluated at a plus j delta x. So what I'm going to do is I'll write out the left-hand sum for this function. So this one would be L5, because we're using 5 rectangles. And this is what it'll look like. Delta x in our case is 0.2. J goes from 0 to 5 minus 1, so this would be 4. And let's see here. Then we just plug in a plus j delta x. And a is 0 in our case, so all we'll have is the square root of 1 minus 0.2j squared. So this would represent the Riemann sum, left-hand Riemann sum for our function here. And all this tells you to do is add up the rectangles from 0 to 4 by plugging in 0, 1, 2, 3, and 4. Okay, for the second example, I already drew these rectangles, and I do have 5 rectangles there. Just one of them has a height of 0. So you'll notice with these, each of these rectangles has a right endpoint, and that's where we're going to take our heights from. And although the last rectangle is not doesn't have a height, so it will have an area of 0, we still have to include it in the sum. So with this one, we can see that if you have a downward or a decreasing function that is concave down, you're always going to have an underestimate, because these rectangles will be, they'll look like this for any concave down decreasing function. So that's what that would look like. Now this one we're not going to calculate, because we're going to do some calculations on the last problem. So in this third example, what we're going to do is create midpoint Riemann sums. So midpoint Riemann sums have the middle of the rectangle touching the function. So if I draw a rectangle, drawing of the rectangles is tedious, but I like that they can be made perfect with this. So then this will have a width of 0.2, because we're still doing the 5. And what we're really looking at is the comparison between left hand, right hand, and midpoint sums. So 0.4, middle point. Okay, that midpoint, actually it's going to move a little bit. And just one more after this. Okay. So the points that are touching the function would be the middle of each of these. So they're fairly close, not perfect. Okay, so if you look at this one in comparison to left hand and right hand, let's just compare it directly to the right hand sums. You can see midpoint is definitely more accurate than the right hand sums above. And if we go back to the first example, midpoint is also more accurate than the left hand sums. Left is an overestimate, right was an underestimate, and then midpoint sums are somewhere in the middle. So if I go back, actually I'll do this one here. I actually forgot to do it on the last one. So the midpoint sum is notated like this. M sub n is going to be delta x, which is the width of each rectangle, from j equals 1 to n. So notice we don't subtract 1. And then it's f of a plus j minus 1/2 delta x. Let me move this out of the way so I don't have to cramp that. Let's put it over here. That's delta x, and that's what you would plug into the function, is all of that. So we're going to do an example of that in just a second. And if I go up to the right-hand sum, I'm going to write out the notation for that one. So this is the right-hand Riemann sum. This would be delta x, and the sum from j equals 1 to n of f of a plus j delta x. And you can see the only difference between the right hand and the left hand is that in the left hand we have an n minus 1. So we have an n minus 1 here. Okay, fourth example we're going to look at. So this will be the last of the Riemann sums of the types that we'll look at. So these are going to be trapezoidal sums. So these are going to have the same width, because that's kind of what we're working with. These are going to be the hardest ones to draw. Okay. So with these, both of the endpoints touch the circle. You can probably already see that the trapezoidal sums are going to be the most accurate. So they're a little more accurate than even the midpoint sums. And the more that you have, the more accurate it's going to be. And that's kind of the point of this. Okay, so for this last one, this would actually be a triangle. There's no way to create a trapezoid in there, so that's what it would look like. So one of the bases would be 0. So with this, just if you don't remember the area of a trapezoid, area of a trapezoid is 1/2 the average of the bases times the height. So 1/2 base 1 plus base 2 times height. Okay, so let's go through these questions here. Of the 4 previous sketches, which gives the best approximation for the area? Well, this is going to be trapezoidal sums. So we've already talked through that. So in the above example, n equals 5, meaning that there were 5 subdivisions. If n equals 10,000, which do you think would provide the best estimate? L of 10,000, R of 10,000, M sub 10,000, or trapezoidal of 10,000. And that's still going to be trapezoidal. You can pretty much see in this that if you had even more divisions of trapezoids, you're going to fill all of this little white space up here under the curve. 10,000 is a lot of those. So the C question is really where we're headed with this. If n were to approach infinity, what would provide the best estimate of A? Well, the best estimate of A would be all of them. So if you have an infinite number of rectangles and triangles and trapezoids and midpoint sums, these would all be equivalent. And this is a conceptual question because obviously we can't draw an infinite number, but you can sort of visualize that. So 6 says calculate A exactly. Okay, well we calculated the left-hand sum and we got 0.859. So if we look at this shape, this is a quarter of a circle, and its radius is 1. So we're going to have 1/4 of the area of a circle, and the radius is 1. So the area of the circle is just pi over 4. Okay, and just to compare it in a decimal form, that's pi over 4. And so this would be approximately 0.785. So as you can see, although that is an estimate in and of itself, the first estimate we did with left-hand sums was 0.859, and we said that was an overestimate, and it clearly is an overestimate. Okay, so for this last example, we're going to approximate the value of the integral, which is the integral from 1 to 4 of x cubed minus 3 dx. Now, we haven't talked about this notation yet, but this integrals, well, I guess we did because we did the antiderivatives. But definite integrals with boundaries, where this upper boundary is 4 and the lower boundary is 1, this would give the exact value of the area between the axis and the curve. But what we're going to do is estimate this with Riemann sums. So delta x in this formula here for the left-hand Riemann sums, because we're going to start with this, is found by taking b minus a over n, and n is the number of subdivisions. So in this case, we would have 4 minus 1 divided by 3. So this would just be 1. So delta x is 1 in this case. So what I'll do is create the L sub 3 Riemann sum notation here. So delta x is 1. I'll put it there even though we don't really need that. And we're going to sum from j equals 0 to n minus 1. And n is 3, so this is 0 to 2. Of f of a plus j delta x. Now this a right here in this case is going to be the a value of 1. So a is 1 in this. So this one will look a little different than the other ones the other one we did. So f of a plus j delta x, we're going to plug all of those things into the function. So I'm going to rewrite this a couple times. So we're going to have a plus, and a is 1. So I'm using x cubed minus 3. So j, so that's a plus j. Delta x is 1. And so we're going to cube this and subtract 3. And that would be, I'm going to clean up that, taking that 1 away. This would represent the sum here. Okay, so that part is, I don't expect a lot of you to understand the summation notation yet, but I'm going to keep talking about it. So let's just go ahead and calculate the area here. So L sub 3. What's the width of each rectangle? Using left-hand sums, it's 1. And then we have 3 subdivisions. So we're going to have 1 and then parentheses. And I'm going to write this using the f of x notation. So this is going to be f of 1, because that's our left-hand side. And then the second value is going to be f of 1 plus delta x. So this would be f of 1 plus 1. And then the last one would be f of 1 plus 1 plus 1. And so left-hand sum would be f of 1 plus f of 2 plus f of 3. And then we just plug those into our function. So f of 1 is going to be negative 2. F of 2 is going to be 5. And f of 3 would be 3 cubed minus 3, so 27 minus 3, or 24. And so we get the value of 27. Okay, so that would represent the area using the left-hand sum, or an estimate of the area. Okay, with this one, I'm going to write out the right-hand sum using sigma notation first. So I'll have r sub 3, because it's 3 divisions. Delta x is the same as the last one, so it's just going to be 1. And this is going to be from j equals 1 to n. And n is the number of subdivisions, so it'll just be 3. And this will look, beyond that, it'll look just like L sub 3. So this will be 1 plus j to the third minus 3. So this would be the summation notation for what we're about to do. Okay, so I will start here. R sub 3 has a width of 1, and then we're going to multiply by all of our widths. So the difference between the left and the right is that we have to, if we start at 1 for the left, then we have to add the width of a rectangle to find out where the right corner would be. So this one would be at f of 1 plus 1. Plus, f of that value plus another one, so f of 3, and then do that one more time for our third sum. Okay, and I know I'm writing those out. I know it seems ridiculous to write ones, but it's to show you that I'm indexing that using the delta x. So this is f of 2 plus f of 3 plus f of 4. So with these, there's a lot of reusing of your work. Above here, we can see right here, this 5 is circled because 5 is f of 2, and f of 3 is 24. F of 4 would be 4 cubed minus 3, which is 61. And we add those together and we get a value of 90 units squared. So if you look at that in comparison to the left-hand sum, it's a very big difference between the left-hand sum. So that should tell you something about whether the function's increasing or decreasing and what your estimates mean in that context. So now let's calculate the midpoint sum. So I'm going to draw a little diagram down here to help visualize what I'm actually doing. So if I have something I have to divide into 3 subdivisions and I start at 1 and at 4, this is what we'd have. So we just need to find the middle of these. And looking at that diagram, it's pretty easy. Between 1 and 2, the middle is halfway between that. So it would be 1.5 would represent here. Between 2 and 3, this would be 2.5. Between 3 and 4, this would be 3.5. So those are the values we're going to evaluate at. And I'm going to turn those into fractions though. So this would be 1, because that's the width of the rectangle, times f of 3 halves plus f of 5 halves plus f of 7 halves. Okay, and then we're just going to calculate each of those. Okay, so I just calculated these. So I have f of 3 halves would be 3/8. And then f of 5 halves, so we're plugging these into the original function, which is x cubed minus 3. So this would be 101 over 8, and this last one would be 319 over 8. So I'm just plugging those into a calculator, getting those values. So we're going to add all those up. So this would be 423 over 8, which is approximately 52.875 units squared. So as you can see, the midpoint is between the right-hand sum and the left-hand sum.